So thank you to everybody who's joined us today for this 1-hour CPD presentation by Brendan Dervan. This event is on behalf of the Electrical Division of Engineers Ireland, and my name is Orla Burke. I'm chair of the Electrical Division. So we are so thrilled that you could join us today. Just like to remind everybody to keep an eye out on the events page of the Engineers Ireland website for upcoming events in the Electrical Division. And also if anybody out there has any topics of particular interest that they'd like us to arrange a presentation on, a webinar, a virtual site visit, please feel free to get in touch. And my details are on the Engineers Ireland website, or I'm sure you can contact Engineers Ireland directly and they'll put you in touch with me. So without further ado, back to today's presentation. The title, as I mentioned, is Data Centers, the Electrical Power System. And we're delighted to welcome Brendan Dervan today to present. Brendan conducts quite a lot of training with Engineers Ireland, and he'll give you an overview of that later. And Brendan is also the Secretary of the Electrical Division, so he's double jobbing. So we'd just like to thank Brendan in advance. So just to give you a bit of an overview, Brendan is a chartered engineer. He's got over 40 years experience in all aspects of mechanical and electrical building services, including design, installation, commissioning and maintenance. After completing an electrical apprenticeship in 1982, he went on to study engineering in DIT. He has worked in M&E consultancy at senior engineer director level since 1990, and in 1999 he started his own M&E consultancy, Dervan Engineering Consultants. His company provided M&E consultancy and project management services to a diverse range of clients in both the public and private sectors. In 2013, Brendan completed an MSc in Energy Management with TU Dublin, and his thesis researched the improvement of energy efficiency in existing data centres. Brendan, as I said, conducts a number of CPD training courses, and you can visit www.besttraining.ie for further information or keep an eye on the Engineers Ireland website. Thank you again, Brendan, in advance, and over to you.
Thanks very much for that introduction, Orla. Nicely summed up. Okay, folks, thank everybody we've a great turnout here today. So thanks to everybody for taking the time out to listen to this presentation. A very important topic. It's actually headlines in the Irish Times this morning. Data centers and the whole issue with connectivity onto the grid and grid congestion and all these issues. So what we're going to look at today is the electrical system, literally from the pylon into the back of the server rack. So what we're looking at here in this image actually is inside a typical data hall, and there are the server racks, and within them you can see there's rows and rows of servers stacked up which consume lots of power. So each of those racks could be typically drawing 20, 30 kilowatts of power, and that converts into heat, and that heat has to be dissipated. So that's where all the power goes in the data center. So we're going to look today at the journey from the pylon right into the back of these server cabinets. So Orla mentioned earlier on that I've retired. It's kind of semi-retirement because I've taken up this role of trainer over the last 2 to 3 years, and I've developed a number of courses. And the reason is I'm kind of passionate about engineering, particularly electrical engineering. That was my field, and I feel, having spent 40 years in the industry, it's worth sharing that knowledge. There's a need for it, and I like doing it. So it's kind of not really like work as such. So I initially developed one main training course on data centers, and I kind of was going to leave it at that because there was a big demand for that. And then I developed the medium voltage course, which there's a big need in that area. There's a big knowledge gap, I suppose, in the building service industry. And I developed a course in that. And then, of course, logically, it followed through on to develop a low voltage distribution course as well. And then I followed off to fill the suite on the data center. I said, you know, uninterruptible power supply systems, or UPS as they're better known. I've a course on that, and then one on standby generators. And that's really those 5 courses is the real data center suite of courses. Incidentally, I've highlighted in red just so I wouldn't forget it, and I nearly did. Orla has mentioned it, that the next date for the data center course is on the 1st of December, next Wednesday week. It's a really, really popular course. It's regularly booked out, fully booked out. It's very, very popular. It covers all aspects of M&E services. Obviously, the main focus would be on the power and cooling systems, and it's very, very popular. So if you want, you can book, I'll remind you of it later at the end, you can book that directly with Engineers Ireland. The other course I do are Fundamentals of M&E Consultancy, which I developed for people coming into the industry, coming out because people are coming into the building service industry from all different career paths now. And it's just to, I suppose, appraise them on the different aspects of what a consultant actually does. The most popular course by far is this bottom left-hand one, the new wiring rules. Came in February of this year. So all new installations have to be designed to the new standard here, which is the bottom left-hand image. And the book beside it is my own guidebook, which I just published. So I'm not here to plug that, but just to let you know, that's a guidebook. It's a kind of it kind of demystifies the wiring rules. They're very, very difficult to read and understand, find your way around them, etc. So the book actually goes through the entire wiring rules and explains them in easier language, I suppose, with lots of diagrams and charts and things like that. And the other two courses, I'm working on those at the moment. I'll be developing those in the coming weeks. The standards for emergency lighting and fire alarm are also going to be updated and changed significantly. So I'll be developing courses on these, which hopefully I'll be running through Engineers Ireland again next year. So without further ado, I'll jump straight into today's topic, which is the electrical power system in data centers. So this little graphic is actually going to sum up what we're going to be talking about today. So obviously we take power from the transmission grid, and it comes through HV switchgear, high voltage switchgear, which is usually owned by the ESB. And we transform down through the transformer here from high voltage down to medium voltage. Now, this whole aspect of it, the connection to the transmission system, the high voltage switchgear and the high voltage transformer, it's usually done as a specialist contract outside of the normal building services contract. So the normal building service engineer that's designed the electrical system in the data center doesn't very often get involved in this. And I won't be either, because it's not my area of expertise. It's really from here down, from the MV switchgear downwards, that the electrical engineer on the data center gets involved in. So the first thing is the MV switchgear, or medium voltage switchgear. Medium voltage is above 1000 volts up to 35,000 volts. So in Ireland, it covers our 10 kV system and our 20 kV system. And it's either one of those two voltages you'd be distributing around the site. So then when you get closer to the data centers, the buildings where the data is being processed, etc., you have to transform back down, obviously, to a safer level of voltage, which is 400 volts. And we transform down to these MV, LV transformers. And you supply into a main board here. So the transformer is usually quite close to the main board. And then you have a generator feeding in. So you obviously have to have a backup generator, because if the grid fails, the show has to keep going in the data center. It's processing all our data, our Facebook pages, WhatsApp messages, and of course, much more important things like banking transactions and all other sorts of things that are running in the background, because everybody runs their business on the cloud now. So that's the diesel generator, provides the kind of long-term backup if there's a long outage. But there's also a UPS system. Now, the UPS is a battery backup system. It stands for uninterruptible power supply. And it basically is a battery backup system that provides a no-break backup to the power system. So if the power fails, the UPS continues to deliver power without even a microsecond of a break. It just continues to feed power to the essential load, which is, of course, the servers. And then the generator starts up, and after about 10 minutes, about 15 seconds, I should say, the generator is online, and it takes over, and the UPS batteries start to recharge again. So this is what we're looking at today, this with the main focus here from the medium voltage switchgear down. And the right-hand graphic is just showing it there. Look, big transmission pile in there, whatever that would be at 220 kV or 110 kV. And the power is going right back into the back of the rack. This is the servers, the back of the server rack. And you can see the power coming in here. The red and blue leads are the cables going up onto the actual servers. And so we're going to talk you through all of that. Right, and the main components in the power system that we'll be looking at there. So medium voltage switchgear, that's what it looks like. So you can see there on the top left-hand image, there's 5 cubicles, we call them. And each of those cubicles is a circuit breaker. So they're the equivalent of the little trip switch in your house, what you call it, an MCB, or the trip switch, some people call it. So that's what each of those are. But obviously, they're handling vast amounts of power. So it's much more complex, much bigger, etc. And then the transformers, which convert the power from high voltage down to lower voltage. That's what we're seeing there. And we'll be looking at that. The generator, so the generator is, that's a typical generator there. You can see the diesel engine is in the middle. It's just the same engine that you have in a big truck or anything like that. Radiator on the end of it, and then it's driving the alternator on the left-hand side. The alternator is just literally a synchronous motor, if you like, and when it's powered by an external source and given some field current, it generates voltage. And that's the generator. And then the UPS system here is, this is what we call a static UPS system. It's stationary. There's no moving parts other than the cooling fans in it. So it converts DC power to AC. So it takes battery power and converts it to AC and gives you a kind of a short-term backup while the generator is starting up. And then the low voltage distribution system. So you can see that board, that's a typical data center board. You can see the length of that. That's probably 30 meters long, that board. And probably, you know, probably £500,000 worth of switchgear in that. So that's the type of thing. As someone quoted once to me, power in data center does not come cheap. It certainly doesn't. So that's what we're going to be talking about anyway. So what's the big issue? Data centers are getting a lot of bad news, a lot of bad press at the moment. Everyone's blaming them on our crisis on the grid, our shortage of power and everything. And obviously they have contributed to it because they're close on, I think, one gigawatt of power heading that direction at the moment. So our maximum demand in the grid in Ireland is about, say, 5.5 gigawatts or something like that. And at the moment, approximately 1 gigawatt of our demand is due to data centers. So some people are saying they're the problem. I think they're really are going to be part of the solution, because the generators are going to be able, because they have inherent backup power systems, they're able to come off the grid at a moment's notice. And that's the whole issue that was in the article in the Irish Times this morning. They're saying that data centers going forward, when they get their contract from EirGrid or ESB, whichever it is, it's going to stipulate that they must have their own emergency backup power system. So there's no surprise in that, because all data centers have emergency backup power systems. But the difference is now they're going to tell them you can have the power, but if we have a demand issue, you know, there's an emergency power issue, we're going to have to take you offline. And they're going to have to sign up to that agreement. And I can't see that being a problem. And I think they should be incentivizing even the older data centers that are here for a long time, incentivizing them to come off the grid at peak times and mitigate that risk that we're facing into at the moment. So what I've shown here, just to explain what the whole issue is, the level of power that a data center takes. If you look in the blue table up here, the top left, it shows you different typical buildings: offices, schools, residential complexes, hospitals. And you can see their power density is quoted usually in watts per square meter. And the square meters obviously refers to the net lettable space on a school, you know, the classroom space. It doesn't include plant room space or anything like that. So it's the net lettable space of the building. So you can see for a fully air-conditioned office building, it's quoted around 82. It'd be more typically around 60 now, because air conditioning processes have changed and they've gone for natural ventilation a lot. So a typical office might be taking 60 watts per square meter of demand, down to something like a hotel might be only 25, or a church or something like that, bank, small building like that, 15 watts. You know, there's hardly any load in it at all. Now, if you look at that, I've just thrown those into the data center ones. Then I've shown down the end, low, medium, and high density, 500 watts per square meter up to 2,000 kilowatts per square meter. If you throw that into the graph, you can see the difference. So a high intensity data center is 2,000 kilowatts. That's 2 megawatts. A big part, 2 kilowatts per square meter, not 2 megawatts. 2 kilowatts per square meter. To put that in perspective, if you can, we can all imagine an electric heater. You can see them in Power City or wherever, Harvey Norman. You know what it's like. Plug in an electric heater and you can feel the heat of it. Imagine just having 20 of them in the one rack, and then thousands of racks in the one building. That's what you're facing. So that's how you end up with typical data center has thousands of kilowatts, which we call megawatts, of course. So I've done a little comparison down here, different buildings. So a medium-sized office, okay, with a net lettable area of 10,000 square meters. So it only includes the office space, the circulation routes, etc. It doesn't include the plant rooms. And the data center that we're looking at then we're looking at the white space. So in a data center, the white space means the area where the data is actually processed. It's like the production line in the factory. It's where all the racks and the servers are. So it doesn't include the electrical plant rooms and the ventilation plant rooms, etc. So two of them, compare them like with like, 10,000 square meters in each case. So 10,000 square meters will be a medium-sized office, like one of the offices you see along the north wall there in the office, you know, banking headquarters, that type of thing. 10,000 square meters, 60 watts per square meters gives you 600 kilowatts, or 0.6 megawatts to get the language right. So we're talking megawatts, right? 0.6. The same floor print for a high intensity data center is 20 megawatts. And that's typically what we're talking with data centers, 20 megawatts. So you can't just connect 20 megawatts on it, get onto the ESB and say, listen, I'm building a data center, can you give me 20 megawatts? And they make a connection under the pathway. It doesn't work like that. When you get to 20 megawatts, you have to take power directly off the transmission grid. So that's the big difference. Whereas anything at 0.6 megawatts, you're coming off the medium voltage network. 20 megawatts, you're at transmission level. So you're connecting at 110 kV or 20 kV, 110 or 220 kV, sorry. So that's what we're talking about. So the typical data center, an overview. Now, these are very simplified schematics. Obviously, there's only so much you can show in a PowerPoint presentation, but you can see what happens here. You have the pylons here. So this is either 110 kV or a 220 kV network, and they literally break into the line and bring it into they build a new substation dedicated to the data center. Now, when I say the data center operator obviously pays for all of this, and it very often develops the substation themselves, what's shown in the green box, but it's the ownership of the ESB. So what you're seeing inside the green box is connection of one pylon comes down through a circuit breaker, that's the box with the X in it, and the other switches then are called what they call disconnects, high voltage disconnects, to be able to isolate the circuit breaker. So you have a circuit breaker on each side, and then both supplies then are coupled through this arrangement here. So it gives the ESB flexibility to do different switching operations. So again, as I say, that's not normally part of the building services consultant's job. And certainly I've never got involved in anything at that level. I'm just showing it at a very simplified level at this stage. So the building service consultant normally starts here on the medium voltage side. So you have the transformers here converting power or transforming power down from 220 kV or 110 kV down to 20 kV. So those transformers are typically 50 megawatt is typically what you might see, 50 megawatts of power each they handle, which is enormous. You know, it's the size of a large town, you know, will be taking that sort of power. And then the supply comes out at medium voltage, and you come into an A board and a B board. And we're going to explain a little bit about resilience and redundancy. Everything is duplicated in data centers. If the A system fails, you have a B system to back up. And it's typically done like this. You have an input circuit breaker, then you have a number of feeders going out, feeding out to your other transformers around the site, and the two boards are coupled together here. So if you want to take one of the transformers out of service, you can join the two boards together, etc. Lots of different configurations. So that's the basic high-level overview of the power system, and we're going to look at these various components, keep drilling down all the way to the back of the rack. So if you see this diagram, I'm just showing as an example, there's 4 supplies on the A side and then 4 supplies on the B side. So in the next diagram, you're going to pick those up and what happens with them. So you can see there's A1, B1, A2, B2, etc. So this is just one. There's multiple ways of doing it, configuring the power system, but this will be fairly typical. This is showing a data center with 4 data halls, and each data hall has 3 transformers feeding it. You can see there, just say data hall 2 there on the top has 3 transformers feeding into it. And each of those transformers are typically something around 3 MVA, 3 megawatts. So that means there's 9 megawatts of power going into that data hall, right? And all that's in it is racks after rack after rack, just full of servers, processing all our data and storing our data and processing it on our, as I say, our WhatsApp messages, our Netflix movies, our bank accounts, everything we do, smart vehicles going forward, smart cities, that's what they're all there for. They're processing all that data and saving it, storing it, and etc. So in this case, you have 3 transformers. So there's about 9 megawatts of capacity going in there, but the servers don't use all the power. So 9 megawatts, if 9 megawatts is going in, there's approximately probably around 6 to 7 megawatts would be used for processing data, and the remainder of the power is used to cool the plant, to cool down the servers. And there's different ways of doing that. We're not going to talk about that today, but you can have air cooling, chilled water, refrigerant cooling. There's all different ways of doing it. And I obviously cover that in the main course, that the data center course I do. So each of the data halls have 3 transformers, so they're kind of really a mirror image of one another. And then you see there's a reserve supply in the middle. So the reserve supply is like your +1, your spare system that you have here. And that spare system then can take the place of any of the other transformers to the left or the right. So if one of the transformers has to come out of service, this reserve supply can be switched in. I haven't shown it on the schematic how it's switched in. We look at that later. It'd be too complex to show on this diagram. And then the other thing you have in a data hall, of course, it's not just all about servers. The servers have to connect with the outside world. And that's why all data centers have, network rooms where the outside fibers come in and they go in and link to all the various data halls. And that's run through the network buildings. And of course, you have admin, then you have meet rooms, toilets, offices, canteen, all the normal things you have in every other building in the data center as well, because they're not all just unmanned. Most of them have permanent staff in them, a small amount of staff in them, and they have to have all the normal other building functions. So let's look at some of the stuff then that appears. So when we looked at the high voltage connection, first of all, there's 2 options. You can see the top image here. That's what we call air insulated switchgear. And it's called air insulated switchgear because literally the conductors are insulated from one another by air. They're typically separated by the phase 1 from phase 2 to phase 3, etc. is separated in air, typically maybe 1.5 to 2 meters apart, as you see there. So the power comes in on the pylons, drops down, and you can see all these insulators, etc. And these are things like current transformers, circuit breakers, disconnect switches, and things like that. So it takes up a vast amount of space, this type of switchgear arrangement. So that's what we call air insulated, or it's called AIS for short. And then gas insulated is the same thing. We're dealing with high voltage, but instead of insulating by air, the conductors are all contained in these enclosures, which are filled with SF6 gas, which of course has a bad name from an environmental point of view. If it leaks, it has a very, very high negative impact on the environment in terms of global warming and ozone depletion and all those things. So for that reason, it has to be very carefully monitored. But the advantage with the gas insulated is it's extremely compact, probably somewhere around 1/3 the space that an air insulated switchgear installation will take up. So again, this is usually built by the data center operator in Facebook and Clonee, which probably a lot of people know about. It's out there just to give you an idea that I worked on the first phase of that, which was 3 buildings, and the first connection was 120 megawatts. That was for phases 1, 2, and 3. They're now on they're building phase 5, I think, or phase 6, if I'm not mistaken. So, and they have a massive big air insulated switchyard like that. And, at this stage, they probably have 200 megawatts of capacity out on the site. So it's just phenomenal. Smaller data centers might go for this air insulated switchgear arrangement, but in either case, it's built by the data center operator and then handed back to EirGrid as opposed to the ESB. So that's really the 2 options when it comes to the high voltage side. Then transforming down, I'm showing 4 different types of transformer here. The top one is where you transform from the high voltage down to medium voltage. So high voltage, just remind you, is either in Ireland is either 220 kV or 110. There's also 38 kV on our system. I don't think there's any data centers connected to 38. I think most of them are connected at either 110, and the Facebook data center is 220 kV. So that's what you have there. Typically, that would be as part of an air insulated switchgear arrangement. You can see the bushings on the transformer here. So the taller ones are the higher voltage. So it comes in here 220,000 volts. 220,000, just think of that, 1,000 times higher than the voltage in your house. And then it goes out the other outside at 20 kV. The one down below then is another data center I worked on. This is out in Clonshock, and this is 110 kV down to 10 kV. So it's a smaller transformer. This one is 20 megawatts. The one above it is 63 megawatts. So that's a typical one that's fed from an underground supply from the ESB, a remote ESB substation. So it's kind of different arrangement. So they're HV to MV transformers. The two on the right then are MV to LV. So transforming from 20 kV or 10 kV down to 400 volts. So 400 volts, 400 230 is the standard voltage we use in commercial, industrial buildings, etc. In your house, as you know, it's 230 volts single phase, but in industrial and commercial buildings, they use 3-phase and it's 400 230. So that's what these transformers transform it down to the final safe voltage that you can distribute it around the building, etc. And the top one is typically about 3 megawatts capacity, and the one down the bottom is, it says 3 megawatts. That's a copy and paste error. It should be probably about 1 megawatt or 1.6 MVA, whatever. So, so translating that into a simple floor plan, what it actually looks like in the data center. So again, I'm showing data center with 4 data halls. I literally made this up out of my head. It doesn't represent any particular data center. You probably will never see a data center like this. But to explain how where all the different equipment goes, I just use as a simple little block diagram. So the outer dashed line here represents the perimeter fence of the data center. So when you arrive up to these places, you can't just throw your leg over the fence and walk up to the data center. They're highly, highly secure environments for obvious reasons. So they usually have a very high protective fence around the perimeter. And then as you come in, you see the 4 green boxes in the center. They represent the data halls, and the kind of cream color at the top, security, admin, meeting rooms, etc. And then on the outer side, then you'll see there's a kind of 2 blue boxes. They're what they call the electrical plant rooms. Now, I'm not showing any cooling here, where the cooling plant room, because the cooling could be on the roof, or it could, you could have a different configuration. The cooling could be around the perimeter of the building, or it could be on the roof. So we're not getting into that today. This is just a notional schematic showing where everything would go. So what we're going to look at is first of all, the top left-hand corner and top right-hand corner, you see HVMV. That's where your transformers would go out. They go out in a compound. So these are massive big transformers, probably 20 megawatt each, or 20 MVA to use the proper term. And they're low cage. You keep them apart from one another in case the proverbial bomb hit one, it wouldn't damage the other, etc. And then somewhere else, which I haven't shown in the schematic, you have the ESB HV substation. This substation that brings the supply in from the pylons, and it's not shown the diagram here because it could be anywhere, it could be any configuration. Some of the sites, the substation is actually remote. The ESB bring cables from their substation into the site. So that's what I'm showing here. See, if the 2 transformers, the A transformer and the B transformer, transform from HV to MV. And then you have your MV switchboard shown in red. You have your A board and your B board. You'll start getting a feel for it very shortly. Everything is duplicated or has a spare reserve system backup. So what we're going to look at now is a typical data hall. I'm going to take data hall 1, for example, and look at what switchgear is associated with that. So you can see to the left of data hall 1, you have 3 gray boxes followed by 3 green boxes, etc. And what they represent is the gray box represents the main LV switchboard. And if you look out from the main LV switchboard, you'll see it's fed with a generator, and the little green box beside it represents the medium voltage to low voltage transformer. So the medium voltage, low voltage transformer has to be right beside the main board, very, very close, because the cables coming off it are absolutely massive. So you try to keep that as close as possible to the switchboard. And likewise with the generator. The red box outside then is the MV switchgear, which feeds the transformers. These green boxes are supplied at 20 kV typically from the red switchboard here. And that module just repeats itself all the way around. So in this case, if you want, the basic building block is about a 3 MVA transformer and a 3 MVA generator feeding into a board. And that board then turn feeds down into the UPS system. And the UPS system then in turn feeds power directly to the server. Well, not directly. There's a whole series of other equipment that feeds through before it gets to the servers, but that's where the servers draw their power from. So the other stuff that would be fed from the board, we haven't shown it here, is the cooling plant and things like lighting, small power, all of those other things that a building needs to function. But our focus today is on the server, so that's all I'm really showing here in it. So you can see that that really is a schematic representation of what we should, a plan version of that schematic really. That's what I was trying to create, that in plan form. Okay, 4 data halls, and each data hall has 3 transformers, 3 generators, and then in the middle you have a reserve. So if any one of these transformers or generator fails, the system is designed so they can pick up power, they can take power off the reserve system here. And we look at that in a few slides, I think. Next one. I didn't realize it was coming up so quickly. Okay, so in this case, I'm showing 3 boards here, then a reserve, then another 3 boards. In the schematic, I'm only showing 2 boards and a reserve just for simplicity. As I say, if I put the 6 in, you wouldn't be able to read the diagram. So this is typically what happens schematically now. We're down at the medium voltage level now and getting in from medium voltage down to low voltage. So we're down a good bit down through the power system at this stage. So you have your transformer convert medium voltage to low voltage. You have your generators feeding into the board. Now, if we look what happens in each board feeds down and feeds through this thing called an ATS. I'll explain about that in a minute. It stands for automatic transfer switch, but the power comes through that and then feeds the UPS system, which feeds the servers. L and SP stands for lighting and small power. So all the lighting in the building, small power, small fans and things like that. And then the MEC, it refers to MEC cooling system. So they're the 3 main loads really you have fed off each board in each data hall: UPS, lighting and small power, and the cooling system, whatever that is, chilled water, fans, whatever it is. Now you'll see each of those 3 loads is fed through the ATS that I refer to. ATS just stands for automatic transfer switch, and an automatic transfer switch just allows you to transfer the power from one source of power to another. Now, in this case, the red is the primary power coming off the main board. Okay, so you can see the next system has a red board as well. And the blue is the reserve. So the blue comes off the reserve system here. And it means if you want to come in and plan, say, I want to take this main board out of service and work on it. Well, I don't want my servers on that off that board to sit down. So what you do is you transfer the power over onto the reserve line. And then you work on MDB1, you service it. Then you work on MDB2 a month later and you service it, and MDB3 and 4, etc. And of course, it also works in the event of a fault. If the system power failed, the first thing it would do is try and start its generator. If the generator didn't work then, well, then it would transfer onto the reserve line. Okay. Now, when we get further down, you will see you come through the UPS. So the UPS, which we'll talk about in a few minutes, the UPS is your battery backup system that converts battery power into AC power, and it's a no-break supply arrangement. And that provides power down to your UPS distribution boards and out to the load. So you see I'm showing A supplies to the rack, then B supplies to the rack, typically. So it means that every rack has an A supply going into it and a B supply. And then every server connects to an A and a B supply. So you're bringing that resilience all the way down right from the HV network, right down to the back of the rack. That has a dual pathway to every single server. If one supply fails, it automatically picks up the supply off the other one. But to make that work on the UPS, we end up having to have a reserve UPS distribution system as well. So the top blue line there represents the power distribution system for mains power, and the bottom blue one coming down this way represents the UPS reserve power system. And you'll see now they go through a similar switch, but in this case, it's not an ATS, it's called an STS. Which means static transfer switch. So it's static, it changes over to an electronic transfer system, which the transfer from one to the other is in the order of milliseconds, maybe a very 3 or 4 milliseconds the transfer is. Whereas with an ATS, it could be 20 or 30 milliseconds. You couldn't have that with critical load. It would see it as an outage and your servers would crash. So that's why if you're doing this arrangement, and this is not the only one, there's hundreds of different ways. This is just one example I'm giving. The critical load is able to draw its supply off this UPS or this one. So that's a typical arrangement. We call that like a tier 3 data center. So tier 3 is usually what they call an N+1 arrangement. So this N+1, which we again will cover in a few slides, means your need +1. So this data hall here is supplied by 2 boards it's a need, and you have one spare system. And in this case, the spare system is shared by another adjacent data hall with MDB 3 and 4 on it. So that's quite a common solution, quite a common architecture, and it's probably the most cost-effective solution, and a lot of the data centers use that or variations of it. Right, so we're going to start looking at a few of the other components on the system now. So generators obviously play a huge part in data centers, and as I said, we were informed in the Irish Times this morning that it's now going to be mandatory, but of course, you take it as read. Every data center has backup generators anyway. They weren't waiting on EirGrid to advise them to put them in. The big difference is they can now, EirGrid will be able to, by law, be able to force them to come off the grid and go onto their standby power, whereas at the moment, they've no obligation to do that. But I think personally, I think they will start engaging with EirGrid and availing of what they call the demand side management, where heavy energy users can come off the grid and assist in mitigating against risks of power failure due to overloading on the grid. And data centers, there'll have to be incentives in place, as we've had for years. We've had a thing called the winter demand reduction incentive. It's been around for decades, where they encouraged big consumers to come off the grid between either reduce their demand or transfer their demand over onto generator between 5 o'clock and 7 o'clock in the winter months, November, December, January, February. And by doing that, EirGrid were avoiding that big peak that occurs when we all arrive home from work, we stick on the oven and the kettle, and you sit down and watch Coronation Street, and you put on the kettle again, or whatever you're up to. If the demand spikes around that time, between 5 and 7 during the winter months, and electric heaters and all that type of thing contribute to it. So they encourage people to come off the grid at that stage, and that's kind of gone now, and they've introduced demand side management. And I think they're going to have to work with the data centers and encourage them, incentivize them to start using their generators at peak periods. So there's typically what the generator looks like. It's it's literally just a big diesel engine. It's a V-form engine, as you can see there. You can see in this one is whatever it is, 6 cylinders on one side, 6 on the other. So it's a 12-cylinder engine, just industrial diesel engine. And this little section in the middle is the alternator. That's where the AC current is generated. And this big box at the end is where the conductors literally come up off the alternator into the circuit breaker. And then you have the control panel here, which controls same way as the dashboard on your car, it tells you oil pressure, the coolant pressure, water coolant pressure, the revs and everything of the engine. So that's all done there. And the other big thing at the end is the radiator, which keeps the engine cooled, and also cools the turbo air for combustion, cools down the air for combustion as well. And that's a very popular make, Caterpillar. We all know Caterpillar engines been around for a long, long time. And here's one that's been made in Ireland for decades. FG Wilson are made up in Larne in outside Belfast, and but they're now owned by Caterpillar, so they're effectively the same company. So some of the considerations, if you're a designer of a data center and you're designing the power system, some of the things you need to consider are, do I go for diesel or a gas engine? That's becoming more and more common, particularly with the new data centers now. They're going to have to run for hours off the grid with their own engines. Diesels, from an environmental point of view, gas engine is better than a diesel engine, but there's a lot of disadvantages with the gas engine. Sizing of the generator, where you go base load, prime, or standby rating is very important. The load transfer arrangement, are you doing a load transfer, or are you synchronizing with the grid? All the generator power and control cabling, how that's done, earthing arrangements. The generator enclosure, do you build dedicated plant rooms? Do you put it on the roof? Do you put it down at ground level, etc.? Ventilation system, they take an enormous amount of air, which isn't shown here in the diagram. So to cool that radiator down, when you're driving your car, you're driving against the wind, so the wind is blowing through your radiator and cooling it down for you. The generator is sitting in a container or in a room, so the fan has to be driven by the engine, and it has to pull in vast volumes of air, which creates lots of noise. So you have to put it through an attenuator to reduce the sound pressure, etc. So there's lots of considerations taken into account. The exhaust system, you can see these data centers now, they're building them all over the place, and they're instantly recognized by the generator flues, the big polished stainless steel flues. You see them popping up over the ridge of the building. They look like warehouses, and all of a sudden you see these shiny chrome flues upside the building, and it's a dead giveaway that it's a data center when you see that. So where you put the exhaust system, how you get up to the building, and then most importantly, fuel storage. So your diesel generator has to have typically 36, 48 hours storage of diesel, which is a massive amount of diesel to store on the site. So it can be bulk stored in a central tank, like in a tank farm, pumped around, which is rarely done, not recommended, obviously, because the whole distribution system becomes a single point of failure. So the alternative is now they're building them with each generator has a tank underneath, a base tank. They're called in the industry belly tanks, but it's just basically a big base tank sitting here, and it just draws the fuel directly off the tank below it. In fact, there's the image on the left is an actual confidential DC site. It's so confidential, I actually don't know myself which one it was. Somebody shared the picture with me, but you can see them there. They're the generators in the containers. So these are normal shipping containers that are used for roll on, roll off type containers. And you can see the flues coming up here, chrome flues coming up, and they're going up this stack here. That's a lattice tower, like it's a triangulated lattice tower. So in this case, it has one flue going up in each of the three sides of the triangle. Okay, and way above the building line there. And then the next three generators goes on to the next flue stack and so on. And then you probably find that that's on one side, just as I showed you in my diagram, and then they have a mirror image of that over the other side of the data center. This one I think is a CGI, but it's you get the drift. It's showing the generators, the flue system going up here, and then you see this big space down here. That's actually the belly tank on it now. So that's the container, the generator in the container, and all of this space below is fuel storage to give you typically 48-hour storage. And the green box here is your fill cabinet where the fuel comes in. That's your fill cabinet, and then you have also what they call fuel polishing system there, because the fuel has to be kept healthy. And what happens in tanks is you get condensation of water, and it leads to microbial growth in the fuel, and it clogs up, just turns into sludge in the end of the tank. And then your generator starts sucking up the sludge and blocks the filters in the generator. So to avoid that, you put in a fuel polishing system, and it gets rid of all that sludge so it doesn't cause engine failure later on. And next step down then is the UPS system. So so just show you what we're looking at here in the diagram. That's actually a small little data center I did about 10 years ago for Aircom, and that is the UPS room in it. So they're the UPS modules on the left-hand side. So each one of those was, as far as I remember, was 400 kVA. So there's 4 of them there. So 3 plus 1, one of them would have been a spare. So your capacity is 3 by 400 kVA, which is 1200 kVA. And then you take power factor, everything into account, and it gives you about a megawatt of power when you take everything into account. And that's all the switchgear. There's quite a lot of switchgear goes into just feeding those 4 modules, feeding the modules, taking the power back off them, and then sending the power out to the servers. And that's the next part of our journey we're going to look at. So in terms of UPS, what do you look at? Reliability and redundancy is important in all aspects of a data center, but it really comes to the fore when you're looking at the UPS system, whether you go for N+1 or 2N level of redundancy. Static systems versus rotary. So the system in the top diagram is a static system. It's electronic components which convert the power to back to AC, and there's the batteries which aren't shown in the diagram because they're stored in a separate room. The battery system is your short-term storage. In a diesel rotary system, which is called a DRUPS, is what they're called, diesel rotary UPS system. That's what you see there on the bottom diagram. So it's a generator at one end, diesel generator, just as we saw in the last diagram. And then you have a flywheel. Now, I'm not going to get into explain how this works. It's a very, very complex piece of machinery, but it's basically a kinetic energy store, okay? So there's 2 rotors, one rotating at 1500 RPM, and there's an outer one running at 3000 RPM. And that kinetic energy store gives you about 10 seconds, 15 seconds maybe of energy storage to allow the diesel engine to start up. So normally the thing is running away, the motor generator part, I should have explained that at the start. The motor generator here is running away and driving this flywheel. It's spinning around, and the power is going into the servers in the normal way. When the power fails, the flywheel continues to run. It continues to drive the motor generator set, which now turns into a generator, and the generator then delivers the power to the load. So the flywheel, as I say, is about 10 to 15 seconds of energy storage in it. And in the meanwhile, the generator starts up, a clutch mechanism closes here and links the diesel set back onto the flywheel, back onto the alternator, and Bob's your uncle. And that's how that works. So they're not very popular, so I wouldn't be worrying too much about them. 99% of the data center market, if not 100% at the moment, is served by static. And these were popular in the 90s and the early 2000s. They were a very popular choice, but the technology has really moved on with static systems. So they are the main player, really. So when it gets to static systems, then there's lots of other consideration with the static system. There's transformer type systems versus transformer-less systems. There's modular versus monoblock, and we will show you a slide in that in a minute. How you operate it, if you operate it online, which means you're sending all your power through the rectifier and inverter, you have certain losses in the system. Most manufacturers offer what they call a high efficiency or eco mode, where you can go into bypass and just feed the load directly, don't go through the inverter. Obviously, there's a risk associated with that, but the savings in a typical hyperscale data center, like you're talking millions and millions of euros just in energy costs per annum, millions and millions of euros just by operating in the eco mode. That's how important it is. And obviously the associated reduction in carbon emissions, there's a lot to be looked at there. Next thing is static and maintenance bypass, how you bypass the UPS, etc. Load power factor and harmonics, etc. Battery systems, the traditional battery is C-lead acid. Lithium ion is now an option, and it's really gaining popularity. The battery analysis and care system, switch room, generator compatibility, and so on. There's a lot to take in, and I'm just looking at the clock as well. I have a few slides to go, and we're approaching question time, so I'll just move on anyway with that. This diagram I mentioned about resilience, and it just shows typically here, if you look top left and you have a load of 200 kVA, as you see in the center. So the 200 kVA represents, say, a data hall with a 200 kVA load, which is not realistic. It would be 2000 kVA maybe. And you decide to use a 100 kVA module. With an N system, you just put in the bare 2 modules, okay? So you have 2 modules. If one of those fails, you've lost the load. So what most data center solutions, the minimum level of resilience is N+1. So they meet the need, they put in 1 spare module. So in this case, you need 3 100s, 2 of them meet the need, and then you have 1 spare one. So that's where that's what the +1 means. The problem with that arrangement is you still only have a single power path into the load. So if the switchgear associated with this UPS system failed, or the main cable, whatever on it, the busbar system in this board failed, you would lose the entire UPS system. So that's why the next one is probably the most popular thing with critical loads, and UPS systems are often done in a 2N configuration, which means you have an A system and a B system, and both systems are capable of meeting your needs. And a step above that, that's used in some of the data centers, is 2N+1. So they have an A system and a B system, and in both systems, they have a spare module as well. So you can see, starting off with a basic need of just 100 kVA modules would meet your 200 kVA demand. You end up putting 6 in. So there's a massive amount of additional plan to put in data centers to meet this resilience element of the design. And the other thing I suggested is monoblock versus modular. So the monoblock is what you see in the right-hand side, and it's sometimes called monolith, meaning the same thing, really. It's a big block UPS. So that, for example, on the right could be a 400 kVA UPS system. The one on the left could also be a 400 kVA UPS system, but just made up of individual modules. So you can see there's 1, 2, 3, 4, 5 modules. So each of those modules will be, let's say, I'll do it the other way around. Let's say it's there 50 kVA, which is fairly typical. So that'd be 5 modules at 50 kVA, giving you a total capacity of 250. And the system on the right is 250 kVA. So this system on the left, this modular way of doing it now, is far better. It's much more energy efficient. You can buy the modules and build it up as time goes on. The availability time is much higher, which means basically if one of these units fails, you literally just whip it out like any piece of equipment. It's plug and play. You whip it out and you replace it with another one. If this unit fails, you have to switch the whole unit down, start pulling parts out, like getting in it, repairing your engine in the car or something. It's a fairly big job. So the downtime of these can be much higher than this system, and as a result, the availability is lower. So for lots of reasons, the industry is moving over to this this modular design arrangement now. And then in terms of switchgear, so the switchgear for the UPS system is typically like this. This system is shown 3 UPS systems, so it's shown in the gray boxes. So each UPS system has a rectifier showing AC coming in one side, DC out the other. Then the battery connects into it there. And then the inverter does the opposite of the rectifier. It converts the DC back to AC and sends that onto the load. And the other little box that you show inside the UPS there with the 2 AC lines in it, that represents what they call the static bypass switch. So if the system gets into trouble or it gets overloaded and the inverter can't handle the load, it transfers over onto this static bypass path here and allows the power to go this way. Okay, so it does a lot more than that, but that's basically what its function is there, that if there's a problem with this power path, it transfers over to here. And this system here, the switchgear, is shown 3 separate UPS modules. And you can see each one has an input breaker on the top, an output breaker, and then item 10 has a complete bypass system on it here. And then this bus bar down the end that you see, all these lines here, they're going out to your, not directly to your service, but going out to the switchgear that in turn feeds your service and our server. And that's where we're coming to in the next slide. So this is typically, I found this slide and I was delighted to find it because it's the exact language I was looking for. And it's the language I don't like using myself. So, but it's what's used here in the industry in Ireland because we're so influenced by what happens in America. Most of the big data center operators here are American. As you know, Microsoft, Google, Facebook, Amazon are all American companies, and many of the colo data centers are as well. They're American operators. So you have the UPS here, and what we're looking at is how do you get power from the UPS to the server. So you don't just bring big heavy cables, you have to go through a series of switchgear systems to get there. So in America, they talk about PDUs, which means power distribution units, and RPPs, remote power panels, etc. The reason they do that way in America, because they have 2 different voltages at low voltage. They have 480, 277 is one voltage system. And then they have a lower voltage again for smaller power, which is 208, 120. We don't have that in Ireland. And really, so the PDU, which has a transformer in it, we're using that term in Ireland, but it's not really a PDU because we don't have a transformer in it. So again, I won't get bogged down with that, but that's the typical arrangement. You come to the UPS through some sort of a switchgear system or a busbar system, and then power is delivered to the server rack. So I'll show you in the next slide here, typically what happens. So in Ireland, the most common solution is to run the power from the UPS system. Just to go back, show you where we're talking about, from these circuit breakers here, item 9, each one of those would feed a busbar system. And the busbar system looks something like this, sitting above the server racks here. So you'll see again, A and a B system. And you can see the A supply comes in this end. You see the box here. The A supply comes in here, but the B supply goes in the opposite end. That's again to avoid the cables coming on the same path to improve resilience. And then the racks on the opposite side of the pod, they have an A and a B supply as well. And there's some other, you can Schneider have a system, PowerBus by E&I up in Donegal, really successful company, just after we probably saw on the paper there a few weeks ago. A small guy, Pat Doherty, started off a small little company 20 years ago, and he sold to the Vertiv for 2 billion euros 3 weeks ago. And I take my hat off to the man, fair play to him. Starting off from small beginnings, and that's just one of the many products that he does. And there's another similar arrangement there. And you can see this is quite a common approach as well. The A supply being in red and the blue supply in the B supply in blue. Red and blue is often used for the A and B supplies. And finally, into the back of the server, we're nearly here, so slightly over time. So the power comes down from the bus bar and it feeds into these power strips. You can see them here. One is in blue again, and one is in red in the back of the server rack. Okay, and they are just like the multi-block you have on your desk with a strip of sockets. It's an intelligent version of that. Okay, so all the sockets are monitored and everything, and the power can be measured through them. And then you take a red lead and a blue lead up to every server. So every single server has an A supply and a B supply to it. And they can come in single phase or 3-phase in 16 amp or 32 amp, giving you a range, a power range for your cabinet from anything from 3.7 kVA up to 22. And I have to say 22 kVA is getting more and more common, 22 kVA in a rack. So basically, that's it, folks, I think. Thank you very much.